17 October 1260. Chartres, France. Below, the cathedral is filled with stone columns, colored glass, and people gathered for its consecration. Above them, beyond the vaulted ceiling, stands another building almost no one can see. A forest of beams suspended high above the nave. The roof appears permanent now. Raising it was anything but certain. This is how medieval builders raised cathedral roofs without modern machines. A cathedral roof began long before the first timber reached the walls. It began in woodland. Carpenters needed trunks suitable for tie beams, rafters, braces, wall plates, and hundreds of smaller members. Some pieces had to span distances far beyond those found in an ordinary house. They also had to support roofing material while resisting rain, wind, snow, and their own weight. At Salisbury Cathedral, parts of the medieval nave roof survived long enough to be studied through tree ring dating. Its principal tie beams reached roughly 42 feet in length. Timbers of that size could not be replaced casually. The longest pieces appear to have been obtained years before they were used, suggesting that builders secured exceptional trunks whenever they became available. But a tree did not arrive as a finished beam. Each trunk curved, narrowed, twisted, or carried knots in a different place. The carpenter had to study what the tree offered and decide what it could safely become. In a yard near the cathedral, workers removed bark and shaped the wood with axes, adzes, and saws. They followed lines marked along the trunk, cutting away material until an irregular tree became a structural member. The surfaces were not polished. They did not need to be. What mattered was the grain, the dimensions, and the joints. Before the roof rose into the air, much of it was organized on the ground. Carpenters laid out major pieces where they could still walk around them. Tie beams formed broad horizontal bases. Rafters inclined toward the future ridge. Posts, collars, and braces connected the larger members. The precise arrangement differed from one cathedral to another. There was no universal medieval roof design. Different regions used different carpentry traditions. Roofs changed over time. Available timber shaped what could be built. A structure over an English nave might not resemble one raised over a French choir. Yet each workshop faced the same fundamental problem. The roof had to carry its load downward without forcing the walls apart. Sloping rafters pushed downward, but they could also press outward at their feet. A tie beam helped restrain that spreading force. Braces stiffened the frame and reduced movement. Repeated trusses divided the roof into a sequence of connected structures. The triangle was not decorative. It controlled force. Medieval carpenters did not calculate these structures with modern engineering software. Their knowledge came through practice, apprenticeship, measurement, templates, and buildings that had already survived or failed. They could read timber. They knew where grain might split, where a joint might loosen, and where a beam would begin to sag. They also knew that hundreds of similar pieces could become useless if assembled in the wrong order. So they marked them. Salisbury's surviving roof contains Roman and Arabic assembly marks associated with different phases of medieval construction. These marks helped identify which pieces belonged together and how they were intended to meet. The roof became a coded system before it became a structure. Mortises were cut to receive tenons. Peg holes were prepared. Matching joints were tested while the timbers remained within reach. A frame could be assembled on the ground to check its fit. It might then be separated into manageable sections or raised in a larger unit if the building, machinery, and timber allowed it. The surviving roofs do not preserve a complete instruction manual. Methods probably changed from site to site, but every method eventually reached the same obstacle. The timber had to move upward. By that stage, cathedral walls could already stand several stories high. Below the future roof were masonry vaults, their upper surfaces curved, uneven, and difficult to cross. Workers needed a temporary construction site above the building. Scaffolding climbed around the walls. Platforms supported workers, tools, ropes, and lifting equipment. Ladders connected different levels. Temporary walkways crossed spaces that would later be sealed in darkness. The cathedral may have survived in stone, but it was built inside a temporary world of timber. Ropes, pulleys, windlasses, and treadwheel hoists could provide the lifting force. A pulley redirected effort. A windlass wound rope around a wooden drum. A treadwheel allowed a worker to turn an axle by walking inside a large wheel. These machines did not remove the weight. They exchanged distance for force. A worker might walk several feet while the rope wound only a short distance around the axle. The beam rose slowly. That was useful. A cathedral timber could be long, uneven, and difficult to balance. Once suspended, it could rotate. Wind could move one end sideways. A rope could shift against the wood. The beam might approach a scaffold at the wrong angle. Speed would only make those problems more dangerous. Before a lift, the crew attached ropes at positions intended to keep the timber stable. Guidelines ran toward workers stationed at different levels. The main rope tightened. The beam lifted only slightly from its supports. Then the crew stopped. Carpenters watched the attachment points. They checked whether the timber remained balanced. They looked for movement near knots, joints, or weak grain. Only after the beam behaved as expected did the lift continue. The people operating the hoist might not see the carpenters waiting above. The carpenters might not see the suspended load until it approached their platform. Signals had to pass through the building. Begin. Slow. Stop. Communication was not separate from the lifting machine. It was one of its working parts. A long tie beam could rise broadly horizontal, guided away from scaffold posts as it climbed. A rafter might travel at an angle closer to its final position. Smaller pieces could be lifted separately or in carefully controlled groups. Reaching roof height solved only the vertical problem. The timber still had to move sideways. Workers pulled guide ropes, while the hoist carried most of the weight. Wooden levers shifted the beam across temporary supports. Over short distances, rollers or smooth-bearing surfaces could reduce friction. The timber moved inches at a time. Wall plates were positioned along the masonry.
It fits well.
Tie beams crossed the building. Rafters rose above them. Braces locked the members into a stable frame. The first major frame was especially vulnerable. Standing alone, it could fall sideways. Temporary ropes and supports held it upright until another frame was raised nearby. Longitudinal timbers connected them. Each additional truss made the growing roof less dependent on temporary support. One triangle was a frame. A sequence of connected triangles became a roof. The operation continued along the cathedral. Lift, guide, position, brace, check the joints, move the equipment, begin again. Notre-Dame de Paris eventually carried one of the most famous medieval roof structures in Europe. Before the fire of 2019, its medieval framework extended for about 100 meters and rose roughly 10 meters above the vaults. Its steep roof reached an inclination of approximately 55 degrees. The structure became known as the Forest. The name reflected the immense number of oak timbers used within it. Yet many medieval members were not monumental beams. The builders used numerous, comparatively slender pieces, arranged into a dense, interconnected system. Strength came not only from the size of one timber, but from the way many timbers supported one another. Above the framework came the outer covering. Depending on place and period, roofers used tile, slate, or lead. At Notre-Dame, the lead covering weighed about 210 tons. That material also had to reach the roof. Sheets were lifted, shaped, joined, and fixed above the vaults. Each new section increased the weight carried by the frame, but also protected the timber and masonry beneath it. Until the covering was finished, weather remained part of the construction. Rain entered open sections. Wind pressed against unfinished frames. A damaged rope could stop a lift. A missing beam could stop an entire sequence. If carpenters had not prepared the next truss, roofers waited. The hoist multiplied human force. Organization multiplied the hoist. Cathedral construction was rarely continuous. Funding failed. Plans changed. Workshops were replaced. Building campaigns stopped and began again under people who had not known the original designers. Salisbury's roof preserves evidence of separate medieval phases. Its timbers record different felling dates, different assembly marks, and periods in which exceptional pieces were stored before use. The structure remembers decisions that written records often lost. A joint shows how a carpenter expected force to travel. A mark shows where a timber belonged. An altered surface shows where the plan changed. But the machines that raised those timbers almost completely disappeared. Ropes decayed. Platforms were dismantled. Hoists were reused. Crane timbers could become part of another building or vanish into firewood. The temporary system was removed, leaving the permanent structure behind. On 17 October 1260, Chartres Cathedral was consecrated beneath its completed roof. The people below could see stone, glass, and vaulting. Above them, hidden in darkness, stood the result of thousands of measured cuts, controlled lifts, repeated signals, and carefully joined pieces of wood. The roof survived. The machinery that placed it there did not. And above the vaults, the timber still holds the shape of a process that has almost vanished from view.